So, in the previous recording on the topic of bioreactors, we ended with this slide where we discussed how bioreactors are being used or applied. First way of using it is to increase the cell number, correct? So here in this slide, we saw that, and as well as to spatially to achieve uniform spatial distribution of the cells throughout the 3D scaffold. Then another role of bioreactor is to maintain optimum level of nutrients and gas concentration throughout the broth in the bioreactor so that all the cells they don't uh, at all face the conditions like hypoxia or toxicity due to accumulation of waste. So there also bioreactors are very much helpful. Then we also saw that people are using bioreactors to provide the scaffold with some stimuli that are naturally present in our body, like compressive forces or tensile forces for development of certain types of tissues like uh, cartilages, bones, etc. Now we will look into what all types of bioreactors people have been using for the tissue engineering application. So the first group of bioreactor is called the stirred bioreactors. And this there will be two types. So first type is the spinner flask bioreactor. So this is the most basic type of bioreactor, all right, which has been used for tissue engineering application. Here, what is happening is that you just need a flask, and within that flask, the scaffolds they are basically hanged using some rods so that they are static, their positions are static, whereas the entire media is circulated. It is not static through the use of a magnetic bar, which is in a rotating condition. So in this way, it creates a perfectly mixed environment inside this particular container. All right, and it so since the media is always in a stirred condition, like it is in flowing condition, so it will not allow cells to form a stagnant layer within the bioreactor. So just as I explained in the previous slide, the same is written here. The scaffold is suspended in needles and then placed in the middle of the flask, while the environment is agitated with a magnetic stirrer, inducing nutrient mix with the scaffold. All right. So this kind of like flow of the media, that is rotational flow of this media, helps in creation of small turbulent eddies. Basically, like turbulent flow takes place, right? So that basically helps the perfect transport of the media through the pores of the scaffold, and then it will allow the media to reach the cells. So it has an added advantage of culturing cells in a static flask. All right, the convention of, but there are some limitations as well, like like the convective flow of the media due to stirring. It it can actually lead to low seeding efficiency, and it can also lead to non-uniform distribution of cells. How? Means as the flow is turbulent because of the rotating magnetic stir bar, it may happen that some of the cells experience some very high amount of shear forces, because of which they can become non-adherent and come out of the scaffold. Okay, so that this if this happens, then it will lead to low seeding efficiencies, like as effective number of cells that you required in the scaffold, it will reduce, as well as distribution of the cells that won't be uniform. So in one part of the scaffold there will be high cell number, another part there will be less cell number. Also, although the pores are there and the convective flow is there, but the rate of mass transfer is not optimum. Okay, that is why it is like this is kind of bioreactors you cannot use for very long experiments like 2 months, 3 months. These are like because of these limitations, the usage of these bioreactors is limited to small period of time. So this slide tells you how this bioreactor has been used in literature. So this bioreactor was used to culture human MSCs, mesenchymal stem cells, on hydroxyapatite scaffold with 500 micron pores. So when they did that, they saw the cell count increase very high, and these cells expressed osteoblastic markers. This bioreactor has been also used for cartilage tissue formation using PLGS scaffold. Again, they were seeded with MSCs and they saw that tubular tracheal graft were formed. Means the MSCs, the differentiated into chondrocytes and ultimate structure, ultimate cartilage construct, it led to it basically developed to become a tubular tracheal graft. Then people have also observed chondrogenic differentiation, means in human adipose stem cells. Okay, and these stem cells were seeded on fibrin gel scaffolds when they were cultured in this bioreactor. So what I mean to say is people have basically changed the differentiation, okay, directed the differentiation of these adipose stem cells, all right, into chondrogenic lineage, and this was achieved when they used this bioreactor. All right. So these were some of the examples that have reported the usage of steered steered bioreactor, okay, steered flask bioreactor. So basically here the concept is the media is being rotated by using a magnetic bar, and while it is being rotated the scaffolds are suspended like they're hanged through a needle. Okay, so similarly, this type of steered flask bioreactor is for lab scale. Now, if you want to do upscale, right, where you're not using 200 or 300 ml of media, rather you want to use thousands of liters of media for growing your scaffolds or growing the cells in your scaffolds. For that, commercially people use steered tank bioreactor. So it is very much similar to the like CSTR bioreactors. I don't know if you have heard about it. Like if any of you have done the course bioreactor analysis, so there are different types of bioreactors. So CSTR, steered continuous steered tank bioreactor. So it is very much similar to this particular class. Okay. So for achieving very high productivity means very large number of cells, and also when you're dealing with large number of scaffolds with cells and large amount of medium, then commercially or in industrial scale people use steered time bioreactors. These systems they can be used to produce RBCs, okay, and if it is I don't know whether it is implemented in clinical setting or not, but if this is being implemented, then you can actually reduce the hospital's dependency on blood donations and keep a sufficient stock. And it has a very similar design with respect to the spinner flask version, where here also the the scaffolds they are basically hanged, okay, they are hanged with some shaft, and this shaft is connected to a motor. So shaft is basically a very long rod. To that, the scaffold will be connected, and this long rod or shaft is connected to a motor. So basically, motor allows it to move. So here we are not using a stirred tank reactor. We are using a physical stirrer. Okay, for so we are not using magnetic bars. Sorry, we are not using magnetic bars because that is for small scale. For large scale, we have to use physical stirrers like blades and propellers will be there that will basically physically move the media. And this kind of stirrers or use of this kind of stirrers in this type of bioreactors, they can help in achieving uniform mass transfer and heat transfer, and as well as homogenize the entire cell culture. Also, the tank is often coated with a thermic mesh, basically an insulator, so that you can maintain a constant temperature of the medium and avoid temperature fluctuations. And the whole system is often covered with several sensors like pH, CO2 level, temperature, etc. So these kind of sensors will let you know in real time what is the critical values of these particular parameters. And in this way, you can control and see how the uh, culture is progressing over a long period of time. So studies using stirred based bioreactors as cell microcarriers for MSCs, they have been used. Okay, for MSCs, these stirred tank bioreactors have been used, and what they have achieved high cell expansion and differentiation, and as well as these bioreactors can be used to monitor their proliferation, metabolic status, then phenotypic expression. So basically, for culturing MSCs, these stirred tank bioreactors have been used. So this is a diagram of how the stirred tank bioreactor should look like. So this is the impeller, all right, and this is the central shaft, and to that there will be impeller blades. So this impeller is connected to a motor, so that that motor will allow movement of this impeller blades, and there will be so this is the medium, all right, culture medium, and you can so here, people in this diagram, the scaffolds are not shown, but yes, you can hang your scaffolds just like in spinner flags bioreactor. And then there is sample port that will let you assess the quality of the media at any point of time, or the quality of the scaffold at any point of time, and to real time monitor the condition of their culture. Uh, there are certain sensors connected to this bioreactor, like the pH sensor, oxygen sensor. Okay, then a CO2 sensor should also be there. Temperature sensor should also be there. So these all components together make a stirred tank bioreactor that is being used for large scale production. Now, so this two slides or these two bioreactors come under a big umbrella of stirred bioreactors, where you're stirring, means mixing, homogeneously mixing the media using a magnetic bar or impeller blades. Now, another class of bioreactor is called rotating wall bioreactor. So, this rotating wall bioreactor was initially developed by NASA. Why? Because they wanted to do cell culture experiments in zero gravity. So and these experiments they wanted to transport to like space, and for doing that they wanted to make sure that the cells and other things they don't feel disturbed. So that is why they developed this bioreactor, this type of bioreactor. Later on, the tissue engineers adopted this bioreactor for culturing various kind of tissues like the cartilage, bone tissue, skin tissue, etc. So here what happens, there is a cylindrical chamber where the wall is able to, so it's a cylindrical big chamber where the wall is able to rotate at a constant angular speed. So it is the outer wall of the cylinder that is rotating, mind it. Okay, we are not using any blades or any impeller to physically mix the media. Rather, we are rotating the outer wall at a constant angular speed. The cylinder wall is rotated at such a speed that it is capable of balancing the three main forces. First is the gravitational force, then there is hydrodynamic dragging force, and there is centrifugal force. And when you are able to balance all three forces, you can actually create a environment where the scaffold can float and will not feel the effect of gravity. Okay, so the scaffolds will float in the media, and they will not settle down by like in the influence of gravity. You are basically balancing out the gravitational force with the hydrodynamic driving force and centrifugal force. So see, the balance of these forces enable the scaffold to remain suspended in cellular environment, taking full advantage of the mass transfer while reducing shear stress. So you are since you are not physically mixing the media, so the scaffold seeded with cells, they will not experience shear due to fluid flow, but the mixing of the fluid is achieved due to rotation of the wall of the cylinder. So the scaffolds which are not near the wall, they will not experience shear, but the scaffolds who happen to go near the wall, they will experience shear. But the media is flowing, right? Media is flowing. So the mass transfer is there. And like uniformity can be obtained by like changing the angular speed of the wall of the cylinder. So if I zoom in, so this is a like rotating wall bioreactor within which you have filled it entirely with the media. This is a central shaft. This has nothing to do. And within this like content within the center of the cylinder, you have added the media along with your scaffolds. So these are the scaffolds. Now you see you are maintaining the speed of the wall of the bioreactor in such a way that you are able to balance out all the three forces. Means the gravitational force is balanced by the centrifugal force and the drag force, because of which the scaffolds they experience a like zero gravity kind of a environment. Means there is no gravitational pull on them, because of which it can float and take full advantage of mass transfer, uniform mass transfer, and less shear stress. This is how it looks like, the bioreactor. So, like this is the cylinder that this is the same cylinder here. It is connected with various kind of supporting structures that helps in maintaining constant angular speed, and like also there will be some sensors as well. So yeah, this is how they look like. And people have actually like this is the basic structure of the rotating ball bioreactor. And depending on what the need is, they have modified their designs as well. So I'll come to that explanation in my next slide. Now, throughout the cell culture, tissue mass and cell number increase inside the bioreactor. That raises the need to increase the rotational speed. So, yes, because of increase in mass, gravitational force will increase. So, you have to then balance out that gravitational force, right? So, because of which you have to then change the uh, angular speed or rotating speed of the cylindrical wall as well. Okay, in order to create that microgravity environment or maintain that microgravity environment. Cellular growth is not always uniform due to rotation, and some scaffold, the capsule scaffold, jump into the wall, causing cellular damage to the culture. In order to overcome that, people have modified this design. So in the previous slide, I showed you now A, B, and C figures. So here B and C. So these two modifications people have done in order to circumvent the challenge that many of the scaffold it can basically hit the wall, because of which the cells they can get damaged, and because of which the cell number will reduce. That is why the modification is there. So how what kind of modification? So people have either like fix the scaffold to the walls or fix the scaffold to the center of the cylinder. So in this way, random movement of the scaffold and random collision of the scaffold with the wall of the cylinder can be avoided. So if you compare this rotating wall bioreactor with the static culture that we do in cell culture flask or with spinner flask assisted culture, rotating wall bioreactor is much better in terms of how the cell are able to proliferate and differentiate. So comparatively, this type of bioreactor, rotating wall bioreactor, is better than the stirred flask bioreactor, stirred bioreactors, and the static culture. So people have done, people have reported in literature the use of this bioreactor for various applications. So first being, um, they have used alginate hydrogen scaffold with the human cartilage progenitor cells and cultured it in this bioreactor. So what they obtained? They obtained elastic cartilage-like tissue. Means the progenitor cells they have differentiated into chondrocytes and secreted the ECM elastin and made artificial tissues that had cartilage-like characteristics. Then people have also cultured scaffolds which are made up of collagen, hydroxyapatite, chondroitin sulfate, okay, and seeded those scaffolds with various chondrocytes like human as well as human derived, bovine as well as human derived chondrocytes. And they reported that this within the scaffolds, type 2 collagen production was enhanced. Then for bone tissue engineering as well, people have used this bioreactor for culturing scaffolds, PLGS scaffolds that were seeded with rat osteoblast, and on doing so, this bioreactor basically enabled them for enhanced cell phenotypic expression and matrix synthesis mineralization. Means, bone is a mineralized architecture, right? So calcium, phosphate, etc. gets deposited. So within the scaffolds, PLGS scaffolds with osteoblast cells, when they were cultured with this bioreactor, rotating wall bioreactor, there was increased synthesis of minerals, right? Calcium phosphate, as well as the uh, like mRNA. When they did mRNA array analysis, etc., they saw that the cells better expressed their phenotype, that is osteoblast phenotype. Now, the third type of bioreactor that we have here is the hollow fiber bioreactor. Now, this type of bioreactor has been used with hepatocytes. What happens? The cells they will be loaded within hydrogel and they will be kept in the lumen of a permeable hollow fiber. So this is a cylinder composed of various hollow fibers, and these hollow fibers they are permeable in nature, means they can allow the passage of media. And within this hollow fiber, the cells are encapsulated within a hydrogen. So it's like a tube. Within that, a gel is there. Within the gel, cells is there, and the entire bioreactor is an assembly of hundreds of these tubes together. The medium is then perfused from one end of the bioreactor. Due to permeability of the hollow fibers, the media reaches the cells that is encapsulated within the hydrogel and like provides the required amount of nutrients and oxygen, etc. And from the other end, the used up media comes out. So this type of bioreactor has been used successfully for maintaining metabolically active cells like hepatocytes. Okay. Then another type of bioreactor that we have is the wave bioreactor. So here what happens, wait a second. No? So in wave bioreactor, we have two main parts. There is platform, and on the top of the platform there is a bag containing your cell mixture, means media and cells. And in this particular bioreactor, we are going to create waves within the cell mixture. Okay, just like in sea beach or in ocean, you see waves. Similarly, we are going to create those waves. Okay, and we can. So this bioreactor looks something like this. This is the platform, and this platform, on the top of the platform there is a bag, and inside the bag is the cell and the media. As you are moving the platform at different angles, okay, and it is happening like periodically, and the motion you can set for how long and at what angle. The rocking, basically the platform is rocking from one end to another end. And in this way, the wave is created within the cell bag. Now we can actually control the wave motion intensity by by controlling the steering of the motor and the platform inclination. Means at what angle you want the platform to move. Then also you can control the speed as well, at how fast you want the platform to like rock. So if you guys have like done practicals and also in labs, there is often such kind of shakers, right? Shakers are available that moves in a similar fashion. And on top of it, you just imagine you have kept a like cylindrical, completely closed bag, and it is like moving from one end to another. It is rocking. Okay. So this wave motion, it is sufficient to provide the cell mixture with oxygen, all right? And people have reported that it can support the growth of more than 10 million cells per ml. The largest advantage is that there is no need of cleaning or sterilizing this bioreactor because we are using disposable cell bags which are pre-sterilized, and because of which when you're trying to do this kind of processes you also uh, bring in risk of contamination if your conditions are not proper. So if you're using pre-sterilized disposable cell bags, then it makes the process simpler. Contamination, it avoids the risk of contamination and makes the process easy. But it is also a disadvantage because these cell bags are expensive, and when you're trying to do small scale reactions, small scale cell culture, then it won't be a good choice. Rather to go for spinner flask bioreactor. But if you are going to go for high scale production, like you are going to grow large number of cells, okay, then you will be able to justify the cost of this cell bag, and will able to get the most of it. Then another type of bioreactor that we have is perfusion bioreactor. These perfusion bioreactors are the ones that better simulate the in vivo environment by providing a flow of medium to the cell culture. Okay, and while the media is flowing, it also provides oxygen and nutrients to the cell-seeded scaffolds. Okay, so these devices they are mostly used in bone and cartilage tissues, and they take advantage of the fact that due to flow of the media, some shear stress is being imposed on the cells. And this kind of shear stress is acting as a stimuli for better growth of that particular cell type. So basically, we are basically capturing the in vivo condition. What happens in our body? The blood flows, right? So the cells which are near the blood, they are like constantly experiencing the shear force due to flow of the blood. So basically capturing that in vitro in a bioreactor form. So the people have seen they have gotten better outcomes when they have used perfusion bioreactor in comparison to stirred flask or rotating vessel bioreactors because perfusion bioreactor they provide higher uniformity in the media, and they also better like stimulate the physical and the environmental conditions on large tissue constructs. Now, these devices can be of various type of configurations, like closed loop, right? Means where the media recirculates, means reused media, it recirculates. The fresh media comes in, okay, gets in contact with the cells and the scaffold, and then the media which is already consumed, it is then recirculated again. So in this way, whatever growth factors or other biomolecules produced by the cells, that also get like circulated uniformly throughout the broth. Whereas also there is single pass where there is continuously the fresh media is coming in and the used media is being removed. So in this way, single pass configuration is also available. So this is how the diagram looks like. So in the first one is basically use means closed loop perfusion bioreactor. The first one is closed loop perfusion bioreactor. So here media is coming from the reservoir and it is being uh, like like coming to the bioreactor, and then the used media it is going back into the reservoir, and again from the same reservoir it is being circulated. So you can see a closed loop is created where the used media is continuously being circulated and kept in contact with the cells and the scaffold. But the second type, there are two types of reservoir. One is the medium reservoir that contains only the fresh media, and there is another tube that removes the used media into a waste reservoir. So this is the media containing the metabolites of the cells, okay, that we are considering as waste, and we are not going to uh, like we are not going to allow that to flow into a cells or scaffold. We are always flowing fresh media to our cells. This is single pass perfusion bioreactor. So the medium flow, it must be optimized in this type of bioreactor because if not, it can cause damage to our cells. Uh, if you are using very high flow rates, then you can cause very high shear stress, and it can also then lead to uh, like the cell. If you are again, if you are using very high flow rates, then the cells won't be able to uh, sense the presence of enough amount of oxygen and nutrients around them. Okay, then they will like experience like conditions like low hypoxia, etc., malnutrition, even if you are throwing fresh media, but you are doing it at a very high flow rate. So that flow rate needs to be optimized. But if you are using low flow rate, then people have actually reported that the cell viability is high in the case of cartilage. Okay, but similar result is not observed for the bone tissue engineering, for the bone tissue engineered constructs. For cartilage, low flow rate works, but for bone constructs, low flow rate does not work. If you're using very high flow rate, then it can also cause cells to de-adhere from the surface, and it will also not allow proper deposition of the ECM molecules, making the entire perfusion system useless. That is why it is suggested that you should use dynamic non-continuous flow. Means you flow the media for few minutes and then you stop it. Okay, give a gap, and then again you flow it, then again you give a gap. So in this way you're flowing, but you're also like allowing the cells to like feel the presence of the fresh media around them. That is fresh, like sense the level of oxygen and the nutrients around them, so that they can absorb it and use it in their metabolic process. Then you remove it, okay, after a certain interval of time. So in this way, you can better increase your cell viability and cell number and uniform cell distribution, and then ultimately see your functional characteristics in your construct. So these are the few references that I used for preparing the lectures on bioreactor. you guys can maybe go through them for more details. And if you guys have any queries, please note them down. We will discuss it in our upcoming doubt clearing session. Meanwhile, please do watch the lectures on bioreactor as well as the host immune response to biomaterials. So these two lectures altogether take up a doubt clearing session. I'll let you know the date and time. Thank you.